Have you ever wondered why some animal or plant populations just seem to explode out of nowhere, while others just fade away? It's one of the biggest puzzles in nature. Well, today, we're going to dig into that story of too many and too few.
Okay, let's just jump right in with two totally opposite stories. On the left, Atlantic cod. Back in 1982, the catch in New England was a whopping 57,000 metric tons. Fast forward to today, and that number has crashed to just over 3,000. That is a massive drop. But on the right, you see the exact opposite. This is an invasive plant called hydrilla, and this map just shows its unstoppable takeover of Florida's waterways. Two totally different outcomes.
So you've got this puzzle, right? One population is crashing, the other is just taking over everything. To figure out what's going on, we have to learn to think like an ecologist. We need to get our hands on the same tools they use to understand any population on the planet.
So let's open up that toolkit. Turns out, ecologists use a few key ideas to get a snapshot of a population's health and its story. And it doesn't matter if you're talking about cod in the ocean or bacteria on an old pumpkin.
First up is the geographic range, and it's pretty much what it sounds like. It's just the area where a population lives. But what's wild is the scale. A bunch of bacteria might live in a space smaller than a shoebox, while the range for Atlantic cod, well, it stretches all the way from Greenland down to North Carolina. That's a huge difference.
All right, next up, population density. This is all about how crowded things are. Think about it like this. You could have a pond with a really low density of ducks swimming on top, but a super high density of fish, snails, and all sorts of critters living just underneath the surface in that same space.
And this is where it gets really cool. Population distribution. This isn't about where they live, but how they space themselves out. Sometimes it's totally random, like these lupine flowers in a meadow. Sometimes it's really uniform, like these penguins who all like to have their own little bit of personal space. And other times, they group together, in clumps, like a school of catfish.
So, what does this all boil down to? When you get right to it, a population size is just a simple balancing act. This picture says it all. You have things that add to the population, births and individuals moving in, which is called immigration. And you have things that take away from it, deaths and individuals moving out, or emigration. If the ins are greater than the outs, guess what? The population grows. Simple as that.
But that makes you wonder, right? What happens if you totally throw that balance off? Like, what if a population had all the food and space it could ever want, with zero predators and zero diseases? What would that kind of crazy, unchecked growth even look like?
Well, the answer is something called exponential growth. And in this perfect fantasyland scenario, the population doesn't just grow, it accelerates. The bigger it gets, the faster it grows, simply because there are more individuals around to reproduce.
If you really want to feel the power of this, get a load of this number. Let's say you start with one single bacterium. It divides every 20 minutes. If you let it go for just one day, 24 hours with nothing to stop it, you end up with 4.7 sextillion bacteria. That number is it's astronomical, from one cell in one day.
And if you were to plot that kind of insane growth on a graph, you get this classic shape, the J-shaped curve. You can see how it starts off kind of slow, but then it just shoots straight up, going almost vertical. That right there is the signature look of exponential growth.
So you see that, and you gotta ask a pretty obvious question, right? If organisms can reproduce this insanely fast, why isn't the whole world just covered in a thick layer of bacteria, or mice, or anything really? Something must be getting in the way.
And that's the perfect question, because it brings us crashing back to the real world. That perfect J-curve can't last forever. In nature, sooner or later reality kicks in, limits happen.
And this brings us to a way more realistic picture of growth, and it's called logistic growth. This is the pattern that pretty much all real populations follow. They might have that initial explosion, but eventually that growth slows way down, and then it just stops.
Let's walk through this, because it happens in 3 phases. Phase 1. This should look familiar, right? It's that same rapid exponential growth we just saw. Resources are everywhere, there's plenty of room, and the population just takes off like a rocket.
But then, things start to change. We hit phase 2. This is the turning point. As the population gets bigger, things get crowded. Food starts getting a little scarcer. Maybe predators notice. The population is still getting bigger, sure, but the rate of growth, how fast it's growing, is slowing down. You can literally see the curve starting to bend.
And that leads us to the final act. Phase 3. Growth just stops.
The growth rate hit 0. At this point, the number of births equals the number of deaths. Everything's in balance. The population size just levels off and kind of hangs out there.
So when you put all three phases together, that idealized J-curve morphs into this, the much more realistic S-shaped curve. This S-shape is the true story of how populations grow in an environment that has real-world limits. Now, see that flat line at the top of the S, that plateau? That has a super important name, carrying capacity. Basically, it's the maximum number of individuals of one species that a particular environment can actually support over a long period of time. It's the ceiling that reality puts on that dream of unlimited growth.
Okay, so we've got our ecologist toolkit, we understand these J-curves, S-curves, and this idea of a carrying capacity. So what? How does this actually help us solve our original mystery about the cod and the hydrilla?
Let's look at them again, but this time with our new vocabulary. The cod? Their population is crashing because the carrying capacity of their ocean environment has probably been lowered a lot. Maybe from overfishing, maybe from climate change. Their numbers are dropping to meet a new, lower limit. Meanwhile, that invasive hydrilla in Florida, it's in a brand new place with tons of food and no natural enemies. It's still in phase 1. It's riding that explosive J-shaped curve of exponential growth. And here's the thing. These ecological rules, they don't just apply to fish and plants. They apply to every single species, including us. And that forces us to ask one last really big question. Every population has a carrying capacity. So, what's ours?